Hello everyone, my name is Long. I'm a scientist in AMES lab. So my drive is not self-driving yet. I'm still driving most of the hardware in the lab. But we have at least some part of them automated. So I will talk about how we were thinking about using AI automation, especially for manufacturing at scale. So talking about manufacturing, especially under the consideration for carbon neutrality by 2050, is a lot of things we have to think about how to develop new projects, new products within limited years. So there are only less than 30 years now, but you probably understand that developing new process takes probably 10 to 20 years. It's how we can use this timeline to develop hundreds of new projects and new products within the limited time is going to be very important. So that's why in the lab, in AMES lab, we've been thinking about how we can go all the way from the lab scale demonstration to low energy, smart manufacturing, especially for carbon neutrality. So one thing we have been thinking about is separate physical modeling. So we will think about how to do reactions in a faster fashion and also even use simulation to generate even more data. And we can put all the data together to help us to inform manufacturing. So there are key questions that we're thinking about. The first one is how should we choose the experimental setup and condition to achieve the desired outcome? And how do I quantify the impact of experimental uncertainty on the outcome? Last but not least, how do I translate lab scale experiments to industrial scale manufacturing? So in this flash talk, it will only cover the first part. So for lab scale demonstration, we have been building this new capabilities in AMES lab. We go all the way from the synthesis, high throughput digitized reactors for synthesizing catalysts and molecules, to high throughput evaluation of their properties for separation catalysis, and then use their data to do AI prediction. So this cycle goes hand in hand. This really helps to do research development and deployment. So as an example, for the digitized reactors, we have mostly using available infrastructure that we can buy, and also simple tubings like switch lock tubing trying to build reactors. We have all kind of pumps, online temperature controllers, online feedback loops using AI, UPLC. We optimize our process for different kind of temperature regions. We can go all the way from -40°C to 400°C for different kind of manufacturing process. We have our own software for the reaction rover that controls all the hardware. We also have the AI enabled reaction optimization functions, so we can use this to do closed loop reaction optimization. So it controls all the hardware and trying to make decisions to optimize reactions. In typical cases, we can optimize reaction within 1 day. So we can also use the data and trying to extrapolate afterwards to see how AI made the decisions during the process. We use the different benchmarking algorithm to understand which algorithm works best for certain reactions and help us to make decisions for the next reactions that we are working on. And also we try to go all the way from a small scale applications to large scales, so we can make molecules or catalysts at a 200-gram scale. We even perform GLC analysis to understand how much better our process or how much greener our process compared to the state of art. Talking about the high throughput experimentation, we mostly employ commercially available CAM-speed systems. We have heard a couple of times yesterday. We have 2 CAM-speed robots now working all the time in the lab. We have all this can be used for hydrogen catalysis, extraction studies, dissolution, leaching, precipitation, crystallization. So this applies to many different industrial process for catalysis and separation. And also we integrate spectrometers, chromatography instruments to the hardware, allowing us to get feedback informations. Also talking about use case, in this case, I will actually talking about one that we use machine learning to inform design of the new molecules for separations. So we train one AI algorithm for 73 elements, 102 metal ions and hydrogen. We try different kind of organic binding molecules, and then trying to use this to help us to design new molecules. On the right, you can see the results. In most cases, the binding is very good, especially for earth elements. If you don't know rare earths, they are very similar to each other in terms of size, and so it's very hard to do separation, especially for adjacent lanthanides. So now with this, our next goal is to design new molecules that can do better separation. So we can apply this to other type of critical minerals. For example, PGMs, gallium, germanium, nickel, cobalt, eventually to lithium, sodium, magnesium. So in this case, in this use case, you can think about, we can apply the closed cycle we have mentioned to do something like this. So we can do automated synthesis of molecules using catalysis applications. Everything is self-optimized. And then with the molecules, we synthesize at a scale, and then we can use them for high throughput automation testing. Without having the molecules at scale, it's hard to do the high throughput studies, which usually take grams of catalysts or molecules. And with all this information, we can screen conditions, screen different catalyst compositions, and trying to get reliable data. And use data to inform AI existing molecular design or catalyst design. So this cycle can go back and forth, and then eventually help us to design a competitive new process. So you can see from this, we employ different type of AI algorithms, different type of automation. As I was saying in the beginning, we do not do fully self-optimizing lab, because you can see that there are very different applications that we ran. It's hard to go all the way from milligram scale applications to gram scale applications. So that's why we are mostly thinking about human in the loop, open loop optimization. So we're definitely looking for new partners to work with us and develop a new process using our testbed facility in the AMES lab. Thank you for your attention.
Thank you.